Swayam Prabha. Digital India. Educated India.
Welcome to the next module in the paper related to Organic Chemistry 2. In this module, we will be studying about reactions of alkyl halide. In the lecture 2, we will be studying about nucleophilic substitution reactions part 2. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The topics that we will be studying in this particular session include factors that affect SN2 reactions, the effect of the nucleophile, and the effect of the leaving group. So these are all the topics which we will be covering in this particular session.
Now, let us look at various factors that affect the SN2 reactions. We have three major components. One is the nucleophile, another one is the leaving group, another one is the substrate. The leaving group is actually present in the substrate. Here, when we talk about substrate, it is basically the steric effect under the neighboring groups we are talking about, because substrate also has the leaving group, but the leaving group ability is very, very crucial for the reaction to occur. So we are studying about this separately. And of course, nucleophile is a separate entity, so we have to look at what are all the different factors that affect the nucleophile. So remember, the stability and the reactivity are generally inversely related to each other. In the case of nucleophile, we will be studying about what is the charge, what is the basicity, and what type of solvents actually favor the nucleophilic substitution reactions, and what is the polarizability of the nucleophile, and what are the different natures of the nucleophile. And in the case of leaving group, the most important one we will be studying about is the electronegativity, and we also will study about the size and resonances, which plays crucial role in the case of leaving group to. So let us look at the charge of the nucleophile. The negative atom has a better reactivity than a neutral atom as long as we have the same central atom. Say for example, if you have the neutral nucleophile, if you say water, the oxygen is the central atom, and we have a hydroxide ion which is negatively charged. So between water and hydroxide ion, the water is a poor nucleophile compared to hydroxide, which is a stronger nucleophile. The same way when we compare with ammonia or amine and NH2 is having a negative charge, so it is a much more stronger nucleophile compared to the neutral amine or ammonia molecules. The same way alcohol is also a very weak nucleophile compared to alkoxide ion. So what we can say is, if there is a negative atom, it is much more stronger nucleophile than the neutral atom as long as we compare with the same central. And when we talk about basicity of the nucleophile, moving across the row, the basicity actually increases, so does the nucleophilicity. So here fluoride ion, so this is how the basicity increases. When basicity increases, the same way the nucleophilicity also increases. We are only considering the second row elements because organic chemistry mainly deals with many of these carbon, nitrogen, oxygen and fluoride or the halides. So we are focusing on here. So carbon is a very strong or a basic nucleophile, whereas fluoride is a very weak nucleophile. And when we talk about the basicity of a nucleophile in a solvent, so what we had seen was separately without the solvent. When we talk about solvent, this is the one you have to always remember. Solvation reduces the nucleophilicity. What does it mean by solvation? Basically, when we say solvation, it is the surrounding of the nucleophile by the solvent molecules. So this is what? This is the fluoride ion which is surrounded by various water or alcohol molecules. This can form hydrogen bond very efficiently. So due to which the nucleophilicity of the fluoride ion is reduced very drastically. So that is why we say fluoride ion is a very weak one compared to iodide in a protic solvent. So this is what you have to remember. Whatever we are talking about is with respect to the protic solvent medium. And if we take about iodide, iodide is so big that only one or two molecules of water or alcohol is solvating it. In other words, iodine is a much stronger nucleophile under these conditions. So the more solvation leads to stronger hydrogen bond. In other words, the nucleophilicity of this F minus reduces in a protic solvent. But when we move to a aprotic solvent, it is the reverse. Here the fluoride is much more stronger nucleophile because under aprotic conditions there is no solvation. So when there is no solvation, this is free to move. So this becomes a very strong nucleophile. So in a polar protic solvents, these are very suitable for SN1 reactions, and aprotic solvents are generally used for SN2 reactions. So this is the important thing you have to remember when we design the reaction. And when we talk about the polarizability of the nucleophile, large and soft nucleophile, say for example big size of iodine reacts very fast because it is easily polarizable, because the distortion of electron cloud is very important for the nucleophilic substitution to occur. And in this particular case, the energy maximum of the transition state is very low, so the reaction occurs very. And if you go to the other side, that is a small and harder nucleophile reacts slower because they are not easily polarized. Because according to HSAB principle also, we can explain the same. The energy maximum in the transition state is very high for the small and hard nucleophiles. So they react slow. And due to the polarizable nature, the good nucleophiles are also good leaving groups because the polarization helps to stabilize the negative charge. So this is one of the reason the negative nucleophiles are very. And when we talk about effect of the leaving group, we have here the basicity of the leaving group is the ability is inversely proportional. That means if it is a stronger base, it is a poor leaving group. That is what these two are inversely proportional. So let us take the second row elements, ammonia and water. So ammonia is basic compared to water. So the basicity is very high here, due to which this is a poor leaving group compared to water molecule. So the increasing leaving group ability is falling this side. So water is a better leaving group, whereas ammonia is more basic. When we talk about the same thing across the column, that is fluoride, halides, fluorides, chlorides, bromides, and iodide, the weak base is the best leaving group. In other words, iodide is the best leaving group because this is a weak base. And these things you have to remember very carefully because there are certain groups which do not undergo substitution very easily. One is a fluoride, hydroxide, that is alcohols, ammonia are the primary amines, alkanes, RH and RR. These do not undergo substitution very easily because we have a very poor leaving group, that is F minus, OH minus or NH2 minus. These are all the very poor leaving groups, so they do not, the top compounds do not undergo substitution that easily. Whereas these compounds undergo substitution very easily because the respective leaving groups are chlorides, bromides or iodides. So these are very easily leaving groups. So these compounds undergo substitutions more effectively. We can also study about the effect of leaving group based on their basicity levels. So the weakest bases are the most stable as anions and hence they are the best leaving group. So here we have a couple of examples which reiterate the same. Iodide I minus is the weakest base with pK of -10 and it is the best leaving group If we go to the other end of the spectrum, we have NH2 minus, which is the most strong base. So that is a very poor leaving group. Between OH minus and NH2 minus, we have the NH2 minus is the most strong base, being the poor leaving group. We have other halides which are having better leaving group ability, and water, acetate anion, ammonia are all moderate leaving groups. So this way, based on the basicity, we can say what is the best leaving group. So let us look at the effect of the leaving group. As we had seen earlier, the electronegativity increases, the ability of the leaving group to leave also increases. So CH3 minus is the worst leaving group compared to F minus, which is the best leaving group. Similarly, as the size increases, the ability of the leaving group to leave also increases. So from F minus, see, if you look at here, I say the F minus is the best one. This is with respect to CH3 minus, F minus is the best leaving group, but not necessarily F minus is the best leaving group compared to I minus. So when we talk about 2 or 3 groups, we are actually talking about the relative ability with respect to something. So we cannot always say OH minus is a poor leaving group or OH minus is a good leaving group, because these are not absolute terms. These are only relative terms. So I minus is the best leaving group amongst all the groups. But there are even better leaving groups like mesylates and tosylates are there, which are even much more better leaving groups than I minus. So there are various groups are there, and relatively we say one group is a better leaving group compared to another under a certain reaction conditions. So as I mentioned earlier, the Fi minus is a very good leaving group, but when we talk about resonance, the mesylate or the methane sulfonate or methyl sulfate ions are much more better leaving groups than I minus. So because of the resonance, these groups are a better leaving groups. And when we talk about the effect of the substrate on the SN2 reaction, the bulkier groups at the site of reaction actually reduces the rate of the reaction, steric hindrance. This we had seen in the case of neopentyl and the tertiary butyl. So that is the same one we are reiterating once again here. So ethoxide is a very small nucleophile, which is a strong one, whereas tertiary butoxide is a strong base, but it is a very poor nucleophile, because nucleophilicity and basicity with respect to size is inversely proportional.
So in summary, we have studied so far about the factors that affect the SN2 reactions, and we also studied about the effect of nucleophiles, basically their charges, the nucleophilicity, the basicity and the polarizability. How do they affect the progress of SN2 reactions or the kinetics of SN2 reactions? We also studied about the effect of leaving group, its basicity, the electronegativity, resonance and size. How does it affect the SN2 reactions? That also we have studied. With this, we conclude this session.